is equal to 2, 5, 6. And B is equal to 7, 4, minus 3. Now here's the question. Is B a linear combination of A1 and A2? Question mark. Is it? If you read this section, you probably already know the answer. Maybe I should do a different example. I'm not going to. Do I have an answer? And not having an answer, can you tell me how I would figure that out? I'll start by giving you a hint. I'm going to rephrase this question. So if B is a linear combination of A1 and A2, then it's some scalar times A1 plus some scalar times A2, right? That's the definition. So the linear combination is. So I'll rephrase this. Can we find the weights x1 and x2, so the couple of scalars, such that x1, A1 plus x2, A2 is equal to B. Don't be thrown by the fact that I'm now using x to represent scalars and a to represent vectors, where over here I was using v to represent vectors and a to represent scalars. The convention to remember is that I'm writing the scalars first, and also I told you that these things were vectors. This is also a question. So what do I do now?
Solve it as a system.
Solve it as a system. Let's see, what is this system? A1 is 1 minus 2 minus 5. And A2 is 2, 5, 6. B is 7, 4, 3. All I've done is replace the names of the vectors with the actual vectors. Well, maybe this is also a name for a vector. The vector is the abstract idea. This is just a way of it. Let's not get into philosophical issues. So let me turn this into let me multiply this through. So what do I get? I get x1 times 1 minus 2x2 minus 5 x3. So what am I doing? X1 is the scalar. That's the point where you're supposed to yell at me. Plus, this is x2 times each of these, so this is 2x2, 5x2, 6x2. All right, this is the vector on the left-hand side. And then the vector on the right-hand side is still the same, so I'm just going to put an equals there. Save myself some more. And now, in order for these two vectors to be equal, maybe I didn't say that. Two vectors are only equal if their entries are equal, because they're defined entirely by their entries. So the only way two vectors can be the same is if they have the same entry. So what I've really ended up with is first time I saw these properties and they talked about this. In this class, Math 322, I took this as an undergrad here at UK. I saw those properties and I just thought, why are we wasting all this time on that? Now I understand. With experience, I came to understand. Yep, right here. Okay. So this is the system that we end up with. Minus 2x1 plus 5x2 equals 4. This is 3 equations. With 2 variables. And if you remember back to our conversations about inconsistent systems, we might be worried that this is inconsistent. We might be worried that this system does not have a solution. Well, let's now that we know the row reduction algorithm, let's put it into practice. Let's turn this into an augmented matrix and solve it. 1 minus 2 minus 5, 2, 5, 6, 7, 4 minus 3. You can breathe a sigh of relief that I no longer have to think about this as a system of equations. All of the implications of what it means to solve that. Now it's just a grid of numbers and I'm just moving them around. So we're going to do some row operations. First one is to eliminate this. So the top row is going to stay the same. This is a nice pivot, 1. I can easily multiply that by 2 and add it to this one. So I get, this is 0, 2 times 1 is, minus 2 is 0, 2 times 2 plus 5 is 9, and then 2 times 7 is 14, plus 4 is 18. And I'll do the same thing here. 5 plus 5 is 0, 10 plus 6, I hope it's 16, and then 37, 35. 35 minus 30 is 32. Now, I'm going to do another row operation to make my life simpler. 1, 2, 7, 0, 1, 2. Multiply. I divided this row by 9, same thing as multiplying by 1/9. I'm allowed to do that. It doesn't change the solutions. Solutions are the same. 0. Should I do the same thing on this row? 16 is half of 32. Why not? Let's do it. I don't think the book does that, but we're not the book. We don't have to follow the book. Okay. Next, do an elimination. And we see immediately that this row minus this row is 0. I'm sorry, the other way around, but it doesn't matter. 0, 1, 2, 0, 0, 0. So that's now, this is now in echelon form. And we can convert it to reduced echelon form by making all of the pivots 1, well they already are, and then using them to eliminate everything above. So now I'm going to do an elimination there. So negative 2 times this. So negative 2 times 1, negative 2, get that there. Negative 2 times 2 is negative 4. So this becomes a 3. 1, 0, 3. 0, 1, 2. 0, 0, 0. Did we find a solution? Yes. Reading it off from the augmented matrix, x1 equals 3, x2 equals 2. And so what do we get? We get that 2 times this, no, 3. 3 times this, plus 2 times this, equals that. And so it is a linear combination of those two. me that this does not just automatically tell me what time it is? Anybody tell me what time it is?
44.
44. 44?
Mm-hmm.
Okay, so we got 6 minutes. I want to, that's a good example. There's lots of this stuff in the book. That's one of the reasons that I emphasize reading the book before you come to class. First of all, I really want you to ask questions. That's really how I would like for these classes to operate. I've just been talking this entire time, right? Probably 45 minutes at this point. So really, I'm here. Ideally, you would be reading this stuff and learning on your own and coming to me for insight that the book can't give you, right? You can't ask the book questions. So I'm going to emphasize that every day and make you really uncomfortable until you do it. This is the final concept, so we just barely put it in. Well, some obvious cases. Every vector is a linear combination of itself. Zero is a linear combination of any vectors, no matter what vectors we choose. Zero is always a linear combination of them because we can always make the weights 0, right? Well, the set of all linear combinations, if we took all the linear combinations possible from a set of vectors, this is called the span. So let V1 up to Vk be vectors. So span of V1, I think maybe the book capitalizes span, but who cares? Does not matter. So this is the symbolism that we're going to use. This thing right here, with the curly braces around it, signifies that this is a set. You've probably seen this notation before, right? It's a set of k different, or possibly different things. It's just a collection of vectors. And then this span that we write on the front of it says all of the linear combinations of that. So this is equal to, in words, all the set of all linear combinations of V1 up to Vk. All right, that's in words. In symbols, this is A1 V1 plus dot 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 A up to plus AK VK, where all the AIs belong to our field, our number system where we can do addition, subtraction, multiplication, and division by everything goes to 0. So this notation says all of these things such that the AIs are in R. All of the linear combinations of the AIs. That's the span. The nature of these courses where we're dealing with a lot of abstract ideas, and a lot of those abstract ideas will be new to you, is that we have to introduce a lot of terminology at the beginning. It's kind of boring. I want to make sure that we talk about it, and I'm trying to squeeze in some examples. An example of an example is, for example, the span of two multiples of each. The sound of the zipper. I know it's time. Right. So the span of two vectors in R3, they're not multiples of each other. So they're two vectors that don't point in the same direction. Right? They're not collinear. You can't see my fingers. They're not collinear. Right? They're different. They go in different directions. Okay, what is the span of two vectors in R3 that are not multiples of each other? Any guesses? So here's one vector, here's another vector. Say I'm looking down on them straight on, right? So they're going out perpendicular to the way I'm looking. No guesses? Yeah.
Is it a plane?
You don't have to raise your hand, by the way, you can just yell it.
Okay. Is it a plane?
It is a plane, absolutely. I can take any point in the plane that's defined by these two lines. I'm sort of begging the question, right? I'm putting my answer into the explanation. These two lines, if I orient myself so I'm looking straight down on them, they're going perpendicular out like this from the direction that I'm looking. Then I can take linear combinations of these. If I want to take any point in this plane now, this point right here, okay? What I do is, well, this is the origin, and so what I can do is I can project this. Let's say this was not a good choice. Let's put this one here. So I project this down onto this vector, and I get this direction. And I project it onto this vector, and I get this much. Let's see. What's the best way to do this? Oh. So now, easier. This vector right here, I'm going to make a line parallel to this, and I'm going to make a line parallel to this, like this. And now that we see that if we take this vector right here and add this vector to it, which is, this is a scalar multiple of this one, this is a scalar multiple of this one, what I have is a parallelogram here, and based on what we were saying geometrically before, if I add these together, I get this vector here. Okay, thank you for indulging me. Remember to come next time with questions, or mentally prepared for me to talk about coming with questions. We'll say 6 feet apart. Okay. Just talk loud.
Yeah. So can the order of values within a certain linear combination of the span vary?
What do you mean?
So like, if I like arbitrarily choose a linear combination of the span, can the scalar values there be different, or do they all match?
Oh no, the choice is arbitrary. So this was our weight. This was the scalar that we were looking at. These were not the same.
Okay, so they can be different in each
Yeah,
combination of a span.
absolutely.
Okay, so there's a lot of combinations of the span.
Oh, yeah,
Okay.
absolutely. Yeah, there's as many as there are real numbers, which is infinite, times as many as there are real numbers, which is again infinite.
Right. And then each entry within the vector is infinite as well.
So the vector, yeah, the choices for the entries in the vector are arbitrary as well. When we define this three-dimensional vector as simply a list of 3 numbers without any restriction on what those numbers can be.
Okay.
Just as long as they come from our number system.
Okay. And then I had a question about one of the properties. Okay, it's property number 2. So I believe I wrote it down right. It's kind of small, but I was wondering if we could do make it equal to a third expression. I have to read that.
V plus U. Yeah, absolutely.
But you can't do that.
Yes.
Okay.
So the justification for that, based solely on our rules, what did we? It was U plus W plus V property of associativity, we can say that this is equal to this, right? We just move these here,
Right, okay.
and then these we swap by commutivity. And what we get is that this, we already knew that this was equal to. Right,
Okay.
and so we get that they're, by this long chain of inequalities, they're all equal.
Okay. Well, I think that's all I had. Thank you.
Yeah, no problem. The alternate explanation was in terms of real numbers,
Okay.
which is how we originally justified these properties. And it's to say that when you add these entry by entry, you have the same expression for each of the entries. And the entries are real numbers, and we know by the properties of real numbers that this is equal to this is equal to this for each of the entries.
Okay.
You see what I'm saying?
Yes, I think so.
Okay.
Good.
Yeah, I appreciate the questions.
Yeah.